All right, so I want to start today's review by looking at the very last example that we did last time. So last time I ended with this example where we were given this matrix A, and we needed to find the inverse of A. Okay. So I went over sort of the general procedure for computing the inverse of a matrix. So what you do is you start with the matrix A and you augment it with an identity matrix. And then you start performing row operations until you've reduced A to an identity matrix. Okay. And then whatever you have on the right-hand side is going to be the inverse of A. Okay. So I want to begin by using this example to sort of make a connection between inverses and also elementary matrices. Okay. So let's see here. Let me reorganize this a little bit because I want a little bit more space. So I'm going to move this up here, move this up here, move this one up here, make it bigger. There you go. And then this is the last one. Okay. And I'm just going to note the operations that we did at each point as well. So we did that. Here we did two more operations. We did this operation here, and then this was the last operation that we did. Okay. So what I'm going to do right now with this example is I'm going to get the elementary matrices corresponding to all of the row operations that we've just performed. Okay. Oh, all right. So just kind of going in order. So the first row operation that we did was row 1 swap with row 3. Okay. And remember to get the corresponding elementary matrix, you can start with the identity matrix. And if you perform your row operation on the identity, that's going to give you the corresponding elementary matrix. So here, just swapping rows 1 and 3 of the identity. That gives us this matrix, and so this would be the elementary matrix that corresponds to swapping row 1 and row 3. Okay. And next, we performed these two row operations. So if you do add row 1 to row 2, whoops. So yeah, here adding row 1 to row 2. That's going to give us a second elementary matrix. It's going to give us a 1 in the 2, 1 position. Okay. Row 3 minus 2 row 1, so I'm not going to write it out, but I'm not going to write it like the row operation, but row 3 minus 2 row 1, if you perform that on the identity, it gives you a negative 2 in the 3, 1 position. Okay. Adding row 3 to row 2 to the identity will give you a 1 in the 2, 3 position. Wait, adding row 3 to row 2. That should actually be, sorry, in the 2, 3 position. There you go. All right, so then next we had these two row operations. So again, I'm just writing out the elementary matrices corresponding to each of the row operations. So row 1 plus 2 row 2 will give me a 2 in the 1, 2 position. So 1, 2 is here. I'm going to put a 2 there. Okay. Row 3 minus 4 row 2. That's going to put a negative 4 in the 3, 2 position. -4 in 3, 2 position. Yeah. Here we did row 2 times -1. So we've just multiplied row 2 of the identity by -1. It's going to give you the 1, -1, 1 on the diagonal. And then the last operation we did was row 1 minus row 3, so that should put a -1 in the 1, 3 position. So row 1, column 3. Okay. All right. So here, these are the elementary matrices corresponding to all of our row operations. And so last time we talked about one of the important characteristics of elementary matrices is that when you multiply a matrix on the left by an elementary matrix, that has the effect of performing the corresponding row operation. Yeah. Okay, so coming back up to here. Okay, so we know we started with A here on the left, and when we perform this row swap, that's equivalent to multiplying A by the corresponding elementary matrix E1 on the left. Okay. So that means this matrix here should be equal to E1 times A, since E1 is the elementary matrix that just swaps rows 1 and 3. Okay. Now likewise, we perform these two row operations next. So that's the same as multiplying by these corresponding elementary matrices. And on the left, so we had E1A, and then if we multiply by E2, followed by E3 on the left, that product should now give us this matrix, okay? And then just continuing, so adding row 3 to row 2, it's the same as multiplying by this elementary matrix, E4. On the left, so we'd have E3, E2, E1A, and then we're going to multiply on the left by E4. So then this product should produce this matrix here. Next, performing these two row operations will be equivalent to multiplying by E6 and 5 on the left of what we had before. And I'm almost at the end. So when we multiply by row 2 by -1, that's equivalent to multiplying on the left by the corresponding elementary matrix, which we called E7. I'll just skip to the end. And then finally, we did this last row operation. It has this as its corresponding elementary matrix. So if we take what we had before and just multiply by E8 on the left, okay, then this product of matrices will give us this identity matrix that we had at the end, okay? Now, because we have this, so this product of elementary matrices, that gives us another matrix. And we have this matrix times A gives us the identity. And so essentially by the definition of matrix inverse, what's the takeaway from this is that this product of elementary matrices should be equal to the inverse of A, okay? So here we have sort of a factorization of the inverse as a product of elementary matrices. Now, we can also express A as a product of elementary matrices as well. So to see how to do that, I'm going to bring up one sort of quick fact about matrix inverses. So the property that I want to mention is if two matrices A and B are both invertible. So if A and B are invertible, then it turns out that their product AB is also invertible. And furthermore, the inverse of AB is equal to B inverse times A inverse. Okay. So notice that you can kind of distribute the inverse into the parentheses, but notice that you kind of also reverse the order of the product. So instead of AB, it's B and then A. This is pretty easy to prove, if you will. So the idea is if you take matrix AB, and if you multiply it by B inverse A inverse, okay. So because matrix multiplication is associative, you can kind of multiply these in any order. So if you start by multiplying A inverse A in the middle, we know that A inverse times A gives you the identity matrix. The identity is like the number 1, and you know multiplying by 1 doesn't do anything. So multiplying by identity doesn't do anything. That's just B inverse times B. And then again, B inverse times B, just by definition of inverse, that's equal to the identity. So because B inverse A inverse, since this multiplies AB to give the identity, it follows that B inverse A inverse must have been the inverse of AB then. Okay. So that's the kind of a short proof of this property. All right, so I bring this up because if we come over to this example that we did just now, if we invert both sides of this equation, we will get that A is the inverse of this product of elementary matrices. And then applying this property about inverses, we can invert the product if we invert each of the elementary matrices and then also reverse the order that they were multiplying in. Okay. Okay. So then when we inverted the product, so E1 inverse became first on the left and E8 inverse became last. So that's just this property that when you inverse a product, you reverse the order. Okay. All right. So then I talked about last time how the inverse of an elementary matrix is also an elementary matrix. And furthermore, that the inverse of an elementary matrix was the elementary matrix corresponding to the inverse row operation. Okay. So one takeaway is that each of these inverses of an elementary matrix is also an elementary matrix. So therefore, we have both A inverse and A itself written as a product of elementary matrices. Okay. And then if you needed to write out the inverse of these elementary matrices, maybe I won't do all of them, but I'll list at least some of them out. Okay, so E1 was just swapping row 1 and row 3. So how do you undo a row swap? You just swap the rows again. So E1 inverse will actually be itself, because swapping row 1 and row 3 would undo itself. So E2 was adding row 1 to row 2. So E2 inverse is going to be subtracting row 1 from row 2. So it's going to give you a -1 in the 2, 1 position. For E3 inverse, it's just going to change the sign of the -2, so it's going to become +2. So instead of subtracting 2 of row 1 from row 3, the inverse of that is to add 2 of row 1 to row 3. And that's why changing the -2 to a +2 gets you the inverse of A3, and then so forth. Okay. All right. So you can get the inverse of each of the elementary matrices, and then that product of this new set of elementary matrices, when you multiply them together in this order, it will produce the matrix A. Okay. All right. Now, I guess the main takeaway from this example, though, probably the main takeaway is that every invertible matrix is a product of elementary matrices. And furthermore, you could say that a matrix will be invertible if and only if it is a product of elementary matrices. Okay. So the proof of this fact, essentially this example kind of illustrates the idea of the proof. So you compute the inverse of A by reducing it to an identity matrix according to this algorithm. The elementary matrices corresponding to those row operations, that product of them gives you the inverse. And then when you invert that product, that gives you the original A as a product of elementary matrices. That's the idea of the proof of this statement. Okay. As for why this factor is important, there are, I guess, some like theorems in linear algebra that maybe concern inverse matrices, and sometimes you can prove those theorems just by proving that they are true for elementary matrices. And it's like once you know that it's true for elementary matrices, you can use the fact that an invertible matrix is just a product of elementary matrices, and you can kind of use that to prove the general result. So there are a few theorems that can be proven that way, and that's kind of one reason why this fact is important. Okay. All right. All right. Let's continue. So the next I want to start talking about the LU factorization. And I'm going to just go ahead and illustrate how the LU factorization works with an example. Well, maybe I'll give a brief idea of how it works first. So what's the idea of the LU factorization? So let's say we have a matrix A, and you perform row operations and reduce it to an upper triangular matrix U. And we've kind of seen how if you get the elementary matrices corresponding to those row operations, that product of elementary matrices times A would produce the upper triangular matrix that you ended up with. So I'm going to take this product and I'm just going to abbreviate it. I'm going to call it M for now. So we have like MA equals U. Now from this equation, if we multiply both sides by M inverse on the left, what happens is M inverse and M, they essentially cancel out. So you just have A on the left, and then you have A as M inverse times U now on the right. And it turns out that this inverse of M, this matrix here, turns out to be a lower triangular matrix, okay? And so because it's lower triangular, we're just gonna rename it as L, and that gives you this factorization of A as a lower triangular matrix times an upper triangular matrix, okay? And so let me illustrate how the procedure is gonna work though with an actual example. You'll find that you actually don't need to write out the elementary matrices to get the LU factorization, okay? So I'll show you how that works in the example. But nevertheless, it may be a good idea to understand that the L comes from these elementary matrices, okay? All right. So let's just take this matrix A here. So A is going to be 1, 1, 0, 3, 5, 1, negative 2, 1, and 4. Okay. So we want to find the LU factorization. So the first thing you want to do is just reduce A to an upper triangular matrix. Now, when you're getting the LU factorization, you don't want to do any row swaps, and you don't want to multiply a row by a number. Just do that if you will. So for LU, you can only do one type of row operation. Okay, so that's kind of important to note. So specifically for LU, you can only add or subtract a multiple of a row to another row. If you try like just multiplying a row by a number, or if you try swapping rows, that throws things off. And we'll talk a little bit about how to adjust the LU factorization if you do need to do row swaps. But yeah, so make sure you're only doing those like elimination type row operations, essentially, okay? So for example, in this problem, like I'm gonna use this one as a pivot. Okay? And I'm gonna do row 2 minus 3 row 1. And I'm gonna do row 3 plus 2 row 1. That'll give me zeros in the first column there. This would be 5 minus 3, 1 minus 0. 1 plus 2 will be 3. And then here, be 4 plus 0, so it'll be 4. Okay. So the next, I want to just take whatever I have next and use that as a pivot. So here I'm going to eliminate the 3 underneath, I have to do row 3 minus 3 halves of row 2 then, okay? Okay, so then for the last entry, you're going to do 4 minus 3 halves. So that's 8 over 2 minus 3 over 2, so it's going to be 5 over 2. All right. So here we've reduced A to an upper triangular matrix. So this is going to be our U in the LU factorization. Now, to get the matrix L that we need in the LU factorization. So I talked about how L is like the inverse of these of this product of elementary matrices, but you can actually get L really easily without looking at the elementary matrices at all. So here's how it works. For matrix L, it's going to have ones on the diagonal. It's lower triangular, so that means there's zeros above the diagonal. And to get the remaining entries, these entries are going to come from your row operations. So the way it works is this row 2 minus 3 row 1, we had this sort of coefficient of -3, if you will. So I'm going to change the sign and make it +3, and I'm going to put it in the 2, 1 position. Likewise, row 3 plus 2, row 1. I'm going to take this +2, I'm going to change it to a -2. I'm going to put it in that 3, 1 position, so row 3, column 1. And then lastly, row 3 minus 3 halves row 2. We have this -3 halves. I'm going to make it +3 halves and put it in the 3, 2 position of matrix L. Okay. And if you do that, then you can check that if you take matrix L and then you multiply it with matrix U, that this product is going to produce the original matrix A. So I'm not going to multiply it out, but if you want, you can maybe pause the video and just check real quick. All right. So I'll make a couple of notes about the LU factorization. So as I noted, so U is upper triangular. L is lower triangular. But you'll maybe notice there is an additional kind of a special property of L, which is that it has ones on the diagonal specifically. So your matrix L will always look something like this. So ones on the diagonal. And to be lower triangular, it means there's zeros up top. U is lower triangular, so it has zeros on the bottom, like that. Although for U, the diagonal entries don't have to be 1, at least not for the LU factorization. So your U will generally look something like this, okay? All right. Okay, so that's kind of nice. So we have a way of factoring a matrix as a product of a lower and an upper triangular matrix. So now let's maybe talk about one of the applications of that. So one of the applications comes in solving a system of equations. So let's suppose we have, an equation ax equals b. And then we have this LU factorization of a. So knowing that a is LU, we can rewrite the left-hand side as LU times x equals b. So just replacing a with the equivalent product LU. Okay, and then because L and U are triangular matrices, it turns out that we can solve for x without doing any elimination. So the way that's going to work is we're going to sort of split this into two steps. So we're going to denote the product ux as a new variable y. So then this equation would look like a Ly equals b. Okay. And we're going to be able to solve this equation. Whoops. Just by doing substitution, okay? So specifically, we'll be doing what they call forward substitution, just similar to backward substitution. Okay. And then, so the idea is you solve Ly equals b for y. And once you solve for y, you can then go back to ux equals y. And since you know what y is now, you can solve for x. Using the usual backward substitution, since it's already upper triangular. And we'll do an example just to illustrate how that works. So it's actually pretty simple, I think, once you see it in action. So let's just do the example. So I'm going to use the matrix A that we have right here. So let's suppose that we had this system of equations, maybe x plus y equals 1. And then let's say we had 3x plus 5y plus 1z equal to 2. And then we had negative 2x plus y plus 4z equals negative 1. Okay. Yeah, so we have the system of equations and we want to solve it, okay? And in case you didn't notice, the coefficient matrix for the system is precisely, the matrix A that we have in this example. So then X is the vector of unknowns, and remember B is the vector for the right-hand side. Okay. All right, so then as I talked about over here, what we're going to do is we're going to create this new system of equations first, Ly equals b. Okay. So matrix L, we have that over here. Okay. Oh, okay. I thought that was supposed to turn red. Maybe there's, okay, there you go. So I'm going to bring that over to here on the left. All right, so we have a L times vector y. Let's just say vector y is y1, y2, y3. And we're going to set that equal to b. So b is vector 1, 2, -1. And here, if we write out the corresponding system of equations, the first row is going to give us the equation y1 equals 1. The second row gives us 3y1 plus y2 equals 2. And then the third equation is -2y1 plus 3 halves y2 plus 1 of y3 equals -1. And essentially, because L is lower triangular, we can easily solve the system by doing forward substitution. So we know y1 is 1. We're going to substitute forward into the next equation. So we're going to have 3 times y1 plus y2 equals 2. So you're going to get y2 is -1. y1 is 1. And then we're going to take what we have for y1 and y2 and substitute forward into the last equation. So we're going to get -2 times y1 plus 3 halves times y2 plus 1 of y3 equal to -1. And if we just move everything over to solve for y3, it's going to add 2, so +1, add 3 halves. It's going to be 5 halves for y3. Okay. All right, so we just solved for y. So then our next step is we're going to create this new system ux equals y. Okay. So with that, here's the matrix U that we found. So I'm going to just copy down what we have. So U times X, where I guess X was the original variables X, Y, Z. And then we're going to set it equal to Y on the right-hand side. And we just solved for Y in part 1, so Y is the vector 1, -1, and 5 halves. Okay. So now we want to solve for X, Y, Z. So if we convert this into a system of equations, you have 1x plus 1y is 1. 2y plus 1z is -1. And then we have 5 halves, z equals 5 halves. So because this is an upper triangular system, you can solve by doing backward substitution. So starting with the last equation, z is equal to 1. And then we'll substitute back into the second equation. 2y plus z equals -1. So that gives you y is -1. And then we'll substitute these back into the first equation to solve for x. So x plus y is 1, so x is equal to 2. Okay. So then this will give us the solution to the original system of equations. Okay. You can check x is 2, y is -1, so x plus y is 1, and then so forth. All right. All right, so then that's the idea of solving a system of equations using the LU factorization. Okay, so with ax equals b, a being LU, you group together the ux into a new variable y, and then you solve ly equals b first. Since L is lower triangular, you can solve that system using forward substitution. Once you know y, you're going to go back to the ux equals y equation, and you'll solve for x using backward substitution. Okay. All right. Okay, so there are some sort of spin-offs of the LU factorization. So one of them is the LDU factorization. So I'm going to touch on that one real quick. Okay. And I'm just going to illustrate how the LDU factorization works using the example that we have here. So let me just take the matrix A that we have again. So here's A. And then let me write down the L and the U that we found for the LU factorization. So that's what we found for the L. And then here's what we found for the U. Okay. And then with these three matrices, we had this factorization A is LU. So for the LDU factorization, so L and the LDU factorization is the same as it was in the LU factorization. So we're good here. I'm going to copy down L. Okay. Now, as for the D and the U, so U is still upper triangular in LDU. D is a diagonal matrix. And the way the D and the U work for LDU, so D, the diagonal matrix, what you're going to do is just take the diagonal entries of the U that you have for LU. Just take those diagonal entries and put them along the diagonals for D. And then you're going to create a new upper triangular matrix for the LDU factorization. The way that's going to work is you're just going to take the original U for LU, and you're going to divide each row by the pivot, so that we're going to divide row 1 by 1. Okay. We're going to divide row 2 by 2. And then we're going to divide row 3 by 5 halves. Okay. So if you do that procedure where you take the U and LU, take the pivots to create a diagonal matrix, and then divide each row by the pivot to get a new upper triangular matrix, then that gets you the LDU factorization of A. Essentially, the way this works is if you multiply the D and the U in LDU, that gives you the U and the LU. Okay. So in other words, like these two actually multiply to give you this guy here. And you can just check that right now if you want to confirm. And so that's how you get this LDU factorization from the LU. Now, what's nice about the LDU factorization, there's kind of two things which are kind of nice about it, I guess. So one thing to notice about the LDU, so both L and U have ones along the diagonal, at least in the LDU factorization. Okay. So that wasn't the case in LU, right? So for the original LU, L has ones on the diagonal, but not U, not necessarily at least. But in LDU, both have ones along the diagonal. So there's just sort of like a nice symmetry in the LDU factorization, which is lacking in the LU. Okay. LDU factorization is also pretty useful in some applications for symmetric matrices. So I'm going to do a little review on what symmetric matrices are now. So a matrix A is symmetric. Oh, well, actually, I guess I need to talk about transpose first then. Okay. So let me introduce the notion of matrix transpose. So the idea is pretty simple. You take any matrix. I'm just going to create random matrix on the spot here. Okay, so here I have this nice 2x3 matrix. Yeah. Let's call it A for the moment. So the transpose of A, which we denote as like A to a power T, if you will, so A transpose. Basically, you take the rows of A and you're going to write them as columns for A transpose. And that's pretty much it. Okay. So just take the rows of A and write them as columns to get A transpose. You can also look at it as take the columns of A and make them the rows for A transpose. Okay. So both perspectives will give you the same result. Okay. All right. So right now, it maybe just seems kind of silly. Like, why would we just, rewrite the rows as columns or whatever? What's the point of that? So I guess the main reason why transpose is important. Okay. So let's say that we have two vectors. Let's say U is vector. Just to keep it small, let's just say it's in 2 dimensions for now. So they have 2 components. Okay. So we have these 2 vectors here, U and V. Now if I take the transpose of U and then I multiply the transpose with V. Now U is a column, so when you transpose it, it becomes a row. So U transpose and times V. And then when you do the usual matrix multiplication of like row times column, it's U1 V1 plus U2 V2. And what you should notice is that U1 V1 plus U2 V2, that is precisely the dot product of the vectors U and V. Okay. So matrix transpose is very closely related to the dot product because of this fact. And so I guess in so much as the dot product is a very important operation, transpose also is important for that then, okay? All right. Now, we said that a matrix A is symmetric if it is equal to its own transpose. Okay. So that's the definition of a symmetric matrix. A is symmetric if it is equal to its own transpose. So just sort of as an example of how that would work. So to be symmetric, it has to be square to start with, because you see that if it's not square, there's no way the transpose will equal the original, because the sizes won't match. Here's what a 3x3 symmetric matrix looks like. So essentially, for a matrix to be symmetric, it has to be symmetric across the diagonal, okay? So you kind of look at the diagonal, it can be anything ADF, but then for it to be symmetric, it's going to be symmetric across the diagonal. You can confirm that A would be equal to its transpose in this case. So essentially its first row is also its first column. Its second row is also its second column, and its third row is also its third column. Okay. So this is for a 3x3, but you can generalize this. So for a square matrix to be symmetric, I guess like visually, it's going to be symmetric across the diagonal. Okay. And for symmetric matrices, something special happens in the LDU decomposition. So I'm going to highlight that in an example. So what happens is that the LDU decomposition becomes an LD L transpose decomposition. So to illustrate that, let's take this symmetric matrix A. It's going to be 1, -1, 2, -1, 2, 0, 2, 0, 3. So what I'm going to do right now with this example is I'm just going to get the LDU decomposition. So to do that, we're just going to start with elimination. So we're going to do row 2 plus row 1, row 3 minus 2, row 1. So here it's going to be +1, 2, it's going to be 2, and 3. No, not 3, -1. Okay. All right, and then I'm going to eliminate this 2 using this 1 as a pivot. So we're going to do row 3 minus 2 of row 2. And that's going to leave us with a -5 at the end there. Okay. Now remember for the LDU decomposition, so the L works the same in both LU and LDU. So it's 1s on the diagonal, 0s above because it's lower triangular. Here we did row 2 plus row 1. So there's kind of like a +1 coefficient there. I'm going to change it to -1, put it in the 2, 1 entry. Row 3 minus 2, row 1 will give us a +2 in the 3, 1 entry. And row 3 minus 2, row 2 gives us a +2 in the 3, 2 entry, and that gets us the matrix L. Now to get the D and the U for LDU, we're going to take these three pivots, if you will, put them along the diagonal for D. And then for matrix U, remember we divide each row by the pivot up here. So we're going to divide row 1 by 1. We're going to divide row 2 by 1. And we're going to divide row 3 by -5. So then that's the LDU decomposition. So we'd have LDU dot product equals A. But notice that the matrix U is actually the transpose of matrix L. Okay. So the first column of L is now the first row of U. The second column of L is now the second row of U. Third column of L is the third row of U. So in fact, the LDU decomposition has become an LDL transpose decomposition. Okay. So this only works for symmetric matrices though. So if you do want to find the LDL transpose for a symmetric matrix, just find the LDU decomposition. The U will naturally turn out to be the transpose of L, okay? So this can be a useful factorization for symmetric matrices in some applications. So that's why we bring it up. Kind of one more thing I want to mention related to LU, but let me just briefly mention a few properties of the transpose. So one property is the transpose of a sum. It's the sum of the transposes. Okay. Now, maybe more importantly is if you try to transpose a product, transposition is kind of similar to inverse. So remember that for inverse, you can inverse each matrix, but then you reverse the order that they were multiplied in. It's the same with transpose. So to transpose a product, you can transpose each matrix, but then you also reverse the order. So instead of AB, it's now BA over here, okay? There's also a property that connects or kind of relates transpose and inverse a little bit. So this property says that if A is invertible, then a transpose is also invertible. And furthermore, the inverse of a transpose turns out to be the transpose of A inverse, okay? It's pretty short, so let me give a quick proof of that third property. It's going to be useful to see a couple of proofs on occasion. So since A is invertible, we know that multiplying A with its inverse will give you the identity matrix. So what we can do is we can transpose both sides of this equation. Now the identity matrix, if you think about it, the identity matrix is a symmetric matrix. So its transpose is itself. Okay, so I transpose is just I. Now on this side, when you transpose this product, we can use the second property. So this transpose of this product is going to be A transpose first, and it's going to be A inverse transposed second, okay? All right, but now, since we have two matrices which multiply to be the identity, that means that these matrices must be each other's inverses. So in particular, A inverse transpose must be the inverse of A transpose. So that's kind of the proof of that fact property there, okay? Okay. So I'm gonna end this review by talking about one more kind of spin-off of the LU decomposition. Just the PA equals LU decomposition or factorization. So I mentioned at the beginning when we started talking about LU, but for LU, you cannot do row swaps. Okay. So if you cannot reduce a matrix A to an upper triangular form, without a row swap, then that matrix A will not have an LU factorization. So as an example, let's say that we have this matrix A, which is going to be 1, 2, 0, 2, 4, -1, -1, 3, 5. So if you were to try to do the elimination to reduce A to an upper triangular matrix, so you would maybe do row 2 minus 2 row 1, row 3 plus row 1. But notice that when you do row 2 minus 2 row 1, you're going to get a 0 in that pivot position. And because you have a 0 in this position, you don't have a pivot that you can use to eliminate further, okay? So yeah, I can't eliminate this 5 because you've got a 0 in this position. So you cannot do an LU factorization for this matrix then. Okay. Now, if we swapped rows though, so in this example, if you did swap row 2 and row 3, that would give you an upper triangular matrix. Okay. So what happens if you had to swap rows? You can't do A equals LU, but we can do something that's almost A equals LU. So namely, we can do this PA equals LU decomposition. So if you need to do a row swap, to reduce A to an upper triangular matrix, you can get this PA equals LU factorization instead. Now for PA equals LU, you want to do your row swap first before you do any elimination, okay? So let's talk about how that works. I'm just going to go off this example that we have. Okay. So right now we need to swap rows because we got a 0 in this sort of pivot position. So what we can maybe do here is swap row 2 with row 3 to start with. Now, as I said earlier, for PA equals LU, you want to do the row swap first. So before I do this elimination, if you will, I'm going to swap the rows first here. So swapping row 2 and row 3 will give us this new matrix. Okay. And now we're going to do elimination. So we'll do row 2 plus row 1, row 3 minus 2, row 1. Okay. And now we've reduced it to this upper triangular matrix, which we'll call U. All right, then we can get the corresponding lower triangular matrix. So it has ones on the diagonal, zeros above the diagonal. And we'll look at these sort of elimination operations to get the remaining entries of L. So row 2 plus row 1, there's kind of a +1 coefficient there. I'm going to change it to a -1, put it in the 2, 1 position. Row 3 minus 2, row 1, change the -2 to a +2, put it in the 3, 1 position. Now we didn't do a third elimination operation to eliminate this entry. It already zeroed out by this operation. Since we didn't need to do anything specific to eliminate this entry, you just put a 0 there, okay? Now, this L and this U does not give us an LU factorization of A. What it does, though, is it gives us an LU factorization for this matrix here, okay? All right. Now, what is this matrix? Well, we obtained this matrix from A by performing this row swap. So if we take the elementary matrix corresponding to this row operation, so if we take the identity matrix and swap rows 2 and 3 of the identity, so then this would be the corresponding elementary matrix to this row swap. And then I remember how doing a row operation on a matrix is equivalent to multiplying that matrix on the left by the corresponding elementary matrix. So in other words, this matrix here is the product PA. So what we did just now is we found an LU factorization for PA. So hence you have PA equals LU. Okay. All right. So I'm just gonna do one final thing in this review. So let me just take the matrix A that we had just now. So from the last example, that's A. And then let's say we had, an equation AX equals B. I think this time I'll call X, X1, X2, X3. And then let's create a right-hand side B. Let's do 4, 9, -4. Okay. So if we want to solve this system of equations, we can solve this by using the PA equals LU decomposition that we found previously. So this is going to be very similar to what we did before, where we kind of do this forward substitution, backward substitution trick to solve the system. Here's kind of the idea. So we're starting with AX equals B. So what we're going to do first is we're going to multiply both sides on the left by P. Okay. So I'm going to go ahead and do that over here. Now we know that when we multiply by P, multiplying by P will just swap row 2 and row 3. Okay. So I'm just going to swap rows 2 and 3. Over here. So that's PA times X. Now we have to multiply both sides of the equation by P in order to preserve the original equation. And again, multiplying by P in this case just swaps row 2 and row 3. So I'm just going to swap these two entries. Okay, so that's PB. Now next we have that PA equals LU. Okay. So then at this point we can solve this the way that we talked about earlier for just an ordinary LU factorization. So the idea was we're going to set UX equal to some vector Y. So now we have Ly equals PB. I'm going to solve this equation for Y using forward substitution. And after solving for Y, you're going to come back to UX equals Y, and you're going to solve that equation for X using backward substitution. Okay. So let's see how that's going to work. So let's take the lower triangular matrix L that we found earlier. And the first thing we have to do is solve Ly equals PB. So Y, we'll just call it Y1, Y2, Y3. And here's PB on this side. And again, because L is lower triangular, if you just write out the corresponding equations, you'll be able to solve for Y with substitution. So we know Y1 is 4. Plug in 4 for Y1 to here. You're going to get Y2 is 0. Okay. And then plug in 4 for Y1 into here as well. You plug in 0 for Y2 if we had a Y2 here. And then solve for Y3. Looks like Y3 will be equal to 1. Okay. So we just solved for the vector y. Now that we know y, we know that y is supposed to be ux. So let's take the upper triangular u that we had. So we're going to have u times x equals y, which we found just now. And then since u is upper triangular, we can easily back substitute to solve for x. So x3 is -1, x3 is -1, x2 is going to be +1, x2 is +1, looks like x1 is going to be 2. Okay, all right. And then you can confirm that this is a solution to the original system of equations up here. Okay. So that's just kind of a way of solving a system of equations using the PA equals LU factorization. Okay. So then next time I'll start talking about vector spaces and subspaces and whatnot. So starting next time, roughly the next couple of weeks, maybe up until your second exam or so, the class will maybe get a little bit more conceptual and a little bit more abstract. So just kind of be prepared for that. And yeah, I'll see you next time.